Okay, welcome back again. Today we are going to introduce a new concept. It's going to help us deal with ODEs that have some sorts of discontinuities. So it's just imagine you have a linear ODE, and let's say the right-hand side, the forcing function out of t, is, let's say, a piecewise defined function like this, right? A piecewise defined function. And we need to be able to handle those type of ODEs because they happen a lot in life, especially in engineering. The approach we are going to take, not necessarily today, but just overall, the approach we're going to take is we're going to apply Laplace to the ODE like we did before, and then we're going to play with the algebra using the table for Laplace, and then use inverse Laplace to get the solution called y of t. The problem, of course, is if you apply Laplace on a piecewise defined function like this one, we need to learn how to handle those because we don't know yet how to find Laplace on some function that looks like these, right? So as a built-in block, we are introducing the Heaviside function. It just returns either 0 or 1. This is the simplest function you can think of, and as you will see, you can build any Heaviside function just based on these returns of 0 and 1. So what it says is the function is 0 when t is less than 0, and it's 1 when t is more than 1. I know sometimes we only work with positive t's, but I'm just keeping it in general. So pretend t is not time, okay? So it looks like this. So if I have h of t minus 1, it just means you're going to shift this one to the right by 1, as you learned from transformations in some basic pre-calc course. So when you shift this to the right, the values are not going to change, obviously, because you just shifted, right? So what happens is, instead of making the switch at 0, you make the switch at 1. So the same thing, it is an open interval to the left and a closed interval to the right of 1, and whose height is 1, okay? Think of this as off, on. This is a binary, or like yes, no, yes, or non-defective, defective. Think of a light bulb. So it's off, and at time equals 0, it turns on, okay? And in here, the switch is going to happen at 1. So if I have h of t minus c, let's just assume c is positive, because I put it on the positive value, the positive side of the t-axis. The same thing happens, right? It just, the switch happens at c, not at 1, not at 0, but it's at c. Now, what if I take this function and I hit it with some f of t? Well, when you multiply f of t by 0, you get 0. And if you multiply f of t by 1, you get f of t. So there is no difference between these two, except that instead of having a constant function called 1, you have some sort of a function called f of t. I don't know how it looks like. I'll put an arrow here because it might go on forever. Okay. So now, a very important difference is this type of functions, okay? What if I have h of t minus 1 minus h of t minus 3? I forgot to write it, so I just put it in here, okay? So this is exactly like this, just except that it starts at 3. It switches at 3. So let me, for the maybe once, just go over it slowly. Notice there are two critical values, 1 and 3. So I put 1 and 3, which means there are three parts. There are three parts to this equation, to this on-off thing. So it's going to be an off, on, off. Why? So if you have an interval where t is less than 1, and then you have the other interval where t is between 1 and 3, and then you have a third interval when t is more than 3. So it's easy to determine these. Now, when t is less than 1, h of t minus 1 is 0. And h of t minus 3 is also 0. So 0 minus 0 gives me 0. When t is between 1 and 3, if it's between 1 and 3, it's clearly more than 1, but less than 3. So you get 1 minus 0. And finally, when t is more than 3, it means it's more than 1 and more than 3. So you do 1 minus 1, and you get 0. And hence, my little graph. Okay, so looking at a difference is actually helpful. So you don't have to do this minus that. You can quickly tell that it's going to be a 0, 1, 0. Okay, it's always going to be a 0, 1, 0, assuming you're basing it on the basic function. If I have a and b, of course I have 3 pieces: this piece, and that piece, because I have 2 points, a and b, and the same thing happens, right? So it's going to be off, and then on, and then off, and these are the conditions. I'm assuming b is more than a, and both of them are more than 0, because I put them on the positive side of the t-axis. Let me put t here, okay? Of course, now if I have this one times f of t, well, you just multiply this by f of t by f of t by f of t. You get 0 and 0 and f of t. And the difference between these two curves is that this one is linear and this one is not. Well, that could be linear, but we don't know. It's just a function, okay? So, now, before I continue, I'm sure you can follow me with these 5 examples or 6, right? What is so hard is to go backwards, okay? That's what you need to think about. So I know you're not going to have a hard time writing this way, but you might experience a little bit of a hard time because the ODE will be given to you in such a way. So the ODE might look something like this. I'll put it in green. So you might say 2y double prime plus ty prime minus y equals something like this. Something like this, right? So we need to be able to solve this ODE, which means we need to rewrite this like this way. So we should, this is what you need to focus on. How do you write this like this? How do you write this like this, okay? That's what's going to help us. Because if I can write this one like this, then when I apply Laplace on both sides, it's easy to apply Laplace on this side, as you will see, okay? So, it's important in mathematics that if you understand a concept, learn how to work backwards. So if I give you, let's say, a rational function and I say graph it, I'm sure you can graph it. But if I give you a graph of a rational function and I say produce a rational function whose graph is what I'm giving you, you need to think twice about it, okay? And if you are able to graph rational functions and produce rational functions based on graphs, then you truly, truly, truly understand rational functions, okay? That is just an example. All right. So now, so here is, I gave you an example. In here I just wrote f of t. So I put t cubed just for fun. I left the same intervals, okay? The ones I did before, 1 and 3, because you already know them. So how would you graph something like this, okay? It's very simple. We know there are 2 critical values called 1 and 3. So there is t less than 1, between 1 and 3, and more than 3. And if you remember, we had 0, 1, 0. Now we have 0, t cubed 0. And it looks like this blue. The green is just so that you see that 2 cubed. Oh my God, I didn't do it properly. That it's this came from the t cubed, but I didn't graph it properly. So it's here, not touching 1, and between 1 and 3 you get a portion of t cubed, right? Portion of t cubed, and then when t is more than 3, it goes back to 0. It's almost like off, and something is happening here. Okay. Now, I thought, okay, what if I want to produce some function here where I get a function t, a function of t, and a g of t. I called it r of t. How can I possibly produce 2 separate functions? Because the reason I'm saying this, because oftentimes what you see is some sort of piecewise like this. 3x minus 1 when x is less than 1, and x squared is when x is more than 1, or something like this, right? just think of, when you took calculus and you're trying to find points of discontinuities and all that stuff. These two functions, they don't have to be the same. They don't have to be 0 and 1. They don't all have to be 0 except one of them, or all 1 except one of them. Oftentimes, we have two separate functions, okay? And so I call them two functions, f and g, and of course, I don't want to call this f because f is being used, so I used r of t. There is a really clever way to express r of t in terms of f of t and g of t in a very simple way. Remember, I'm trying to go back from here to here. If I give you this, can you give me this? If I give you this, can you give me this? If I give you this, can you give me this? And this seems to be very hard. If I give you this, can you write it like that? And the answer is yes, you can. Okay? And here is how it works. And it's thanks to zeros and ones. Zeros and ones are beautiful because when you multiply something by 0, you get 0. And when you multiply it by 1, you get itself. So I can write this r of t as a function of f and g anytime I want. And it is written in this format. And let's think about it. It's f of t plus, you hit this difference with the Heaviside, where the term changes at c, obviously. So you have to have h of t minus c for sure. Just like you have to have h of t minus 1 and h of t minus 3, we know we're going to have h of t minus c. And here is how it works. If t is less than c, right? If t is less than c, what happens to h of t minus c? It's 0. And when t is more than c, h of t minus c is 1. That's by definition, just by shifting this one. Okay? So keep this in mind. Now, when t is less than c, h of t minus c is 0. So 0 killed this whole piece. So r of t is just f of t. When t is more than c, this quantity is 1. Right? So I inserted a minus so I can kill this f of t. F of t minus f of t is gone, and you're left with g of t because this is 1. This is 1. So anytime you have this, feel free to use this. This is always what is going to be hard for you to do, to write the piecewise defined function in this format before we apply Laplace, okay? So I thought, this would be helpful to you. Now, I'm going to do an example. So somebody gives me this function. Pretend this is the right-hand side of an ODE, okay? And this is like f of t and g of t, okay? Now, so let's say we have, I'll put it in red. Let's say we have an ODE, a1 of t, y prime, y double prime, plus a0 of t, y equals this function f of t. This one, okay? So generally what we're going to do is we're going to apply Laplace on both sides, which we're not going to do today. I know you know how to apply Laplace on this piece. How do you apply Laplace on that piece? That's what I want to do today. I'm going to show you how to do this in two ways. Once, and then we will only use Laplace, okay? So that's what I'm heading at. I want to know how to find Laplace of this right-hand side of this ODE, okay? So method number one, which I never want you to do again, but it's good to see it once, is to use the definition of Laplace. Laplace of f of t is the integral from 0 to 2 e to the negative st f of t, right? You know this, right? Plus the integral from 2 to infinity e to the negative st my function. So this is just the definition of Laplace. And I really never want you to use the integrals anymore. I'm going to show you a better way, okay? So now, I don't know how to deal with limits of integration from 0 to 2. We like 0 to infinity, right? Or even 2 to infinity, but we don't like 0 to 2. So I'm going to write 0 to 2 as 0 to infinity minus 2 to infinity. Here is what I mean. If I want to go from 0 to 2, I can go from 0 to infinity, and I can subtract 2 to infinity. If I do this minus this, I get the leftover, which is that, okay? So I rewrote this, this way. Exactly the same copy, but the limits of integration have changed. And that remained the same. Now, these two happen to have the same limits of integration, so I decided to combine them. So you get 4t minus 2t minus 1 times e to the negative st, I pulled it out, dt, it's from 2 to infinity. So this piece here is this piece. And that is just Laplace of 2t minus 1. Isn't that true? Isn't Laplace of 2t minus 1 the integral from 0 to infinity e to negative st f of t? So, and we know how to do this, don't we? We know how to apply Laplace and get the s's, the letter s, okay? Now, when I subtract these two and I clean this up, I get 2t plus 1. So it looks like I'm almost done because we know this is Laplace, done. But this one looks like Laplace, e to negative s of t, f of t. But it's not. This is not Laplace of 2t plus 1 because this doesn't start with 0. It starts with 2. So I have to change variables, okay? So remember, this is t equals, it's good to do this, t equals 2, t approaches infinity. Okay. So I have t equals 2. I don't like 2. I like 0. So we're going to do t minus 2, and we're going to call it u. So now, if t is 2, then u is 0. So I succeeded. If t goes to infinity, then u also goes to infinity. So that doesn't change. That's good. And of course, I have to change the variables. Every time I see a t, I call it u plus 2. So instead of saying t, I call it u plus 2. And t, I called it u plus 2. I went a little fast here. This is 2, u plus 2 plus 1, this piece. Okay, which is what? 2u plus 4 plus 1. It's 2u plus 5. Okay? So just a little change of the variables. I don't like the letter u. I'm going to go back to t. It's just a dummy variable, so I can just call that t. So here is what I am. Okay? That is exactly this. Except that I used t instead of u. Okay? Now, I think I made a mistake. No, I didn't. Okay, so I went a little fast. This is e to the negative su times e to the negative s 2s. E to the negative 2s went out because this is a function of u. So e to the negative 2s went out. Here it is. And this is e to the negative su. I went back to t. Not that t, but just another t. It's just a dummy variable. So it's e to the negative st, 2t plus 5 dt. Notice that dt and du are the same. You may notice du is also dt, right? So that didn't change. Okay. So I hope that's the first piece we got, and that went out, and that's this. So go back and make sure that you know that this is exactly this. Okay, I'm almost done because now I have 0 to infinity. Now that's Laplace, that's a constant, and this is by definition Laplace of 2t plus 5. And therefore we know how to behave. Laplace of a difference is the difference of Laplace, and the 2 comes out. 2 Laplace of t minus Laplace of 1 plus e to the negative 2s parentheses twice Laplace of t plus Laplace of 5, or 5 Laplace of 1. And you know each one of these, don't you, from the table. Laplace of t is 1 over s squared, hit it with 2. Laplace of 1 is 1 over s with a minus, that stays. Laplace of t is 1 over s squared, but there is a 2. And Laplace of 1 is just 1 over s with a 5 gives you 5 over s. And this is how I would apply Laplace to this function. Okay. Now, of course, next time we're gonna do inverse Laplace to get the solution to the ODE, but for now we're going to stop here. Now this method that I just shared with you, this whole method up to here, all I did is I used the definition of Laplace, didn't I? And the definition of Laplace involves integrals. And we really don't want to deal with integrals. So I don't want you to do this again. But it's good to do it once or twice for homework, but then don't do it again. I'm going to show you another method. And because this is getting long, I'm going to give you an equation. I was going to prove it today, but then it's going to make the video very long. So we're going to use this in green to be proven next time. We're going to rely on this to try to use a different method. So my function is this. The first thing you need to do, as I said, you need to write it in a format like this. And let's see if we can pull it. It's some function times h of t minus 0 minus h of t minus 2. Isn't that true? It starts at 0. Think of this. This might be a little hard. Think of this as h of t minus 0. So it starts at 0 and it ends at 2. Okay? Plus 4t, just h of t minus 2, because it doesn't end. If you can write this like this, you will never have a problem, okay? Because that is the hardest thing to do. Okay. Once you write it this way, I'm going to clean it up before I apply Laplace. I mean, why would you want to apply Laplace right now? You want to clean it up. So this times this, minus this times that, plus this times this. Notice h of t minus 2 shows up twice. So I'm going to factor. So this is 4t minus 2t minus 1, and that stays. This stays. Here it is. And this factor out h of t minus 2 times 4t minus 2t in parentheses minus 1. And I got 2t plus 1 because the minus was outside. Minus 1 is plus 1. Okay? Now that this looks clean, now I'm going to apply Laplace. But I'm going to rely on this. I truly was going to do this on this video today, but it's just going to make the video much longer. What this says is Laplace of h of t minus c times any function is e to the negative cs Laplace of h of t plus c. Okay, you don't have to understand where this came from. We will prove it. In fact, for homework I gave you something simpler to prove, which is also in your book. It won't take us more than 5 minutes. So we're going to rely on this fact. So if I apply Laplace on this, I get Laplace on this plus Laplace of that. Okay. Now, if you look at here, c is 0. Isn't that true? And g of t is 2t minus 1. And therefore, the answer is e to the negative 0s Laplace of this one. Now, this is g of t, right? G of t is this, right? But the answer is e to the negative cs, which is this, Laplace of g of t plus c. Now, Laplace of g of t plus c happens to be 2 times t plus c minus 1. Every time you see a t, every time you see a t, you replace it by t plus c. Okay? And then don't forget your minus 1. Next one. I'm trying to find Laplace of this. Notice that c is 2. So the answer is e to the negative 2s. And then g of t was 2t plus 1. But I want to write g of t plus c. So every time I see a t, I'm going to replace it by t plus c. So every time I see a t, I'm going to replace it by t plus c. 2 remains, and the plus 1 remains. Okay? So hopefully you know that this is this based on the green. Okay? Now, Now C is 2. Don't forget that. For this one, C is 2. For this one, C is 0. So that died completely. So you end up with Laplace of 2t minus 1 because C is 0. Don't forget that. And in here, C is 2. So 2t plus 2 plus 1 is plus 5, right? 4 plus 1 is 5. And e to the negative 2s. And isn't this what we got here? Laplace of 2t minus 1 plus this quantity, Laplace of 2t plus 5. Laplace of 2t minus 1 plus this quantity, Laplace of 2t plus 5. Again, I just did the same thing I did here. I don't need to waste your time. And you should get the same answer. Okay? So the one thing we haven't done yet is to prove this, because without this, we can't function. We can't apply Laplace on this. The second thing is to be able to write this in this format. If you can't write this in this format, you're not going to be able to apply Laplace. Okay? So for homework, I'm going to give you a smaller, a more basic version of this. Notice there is no g of t. Okay? And I would like you to show that this is just that. In fact, if we had proven this, then you get this one for free, don't you? Because g of t is just 1. Okay? So you get Laplace of h of t minus c times 1 equals e to the negative cs Laplace of 1. And Laplace of 1 is 1 over s. And that's why this is true. So, repeat. If I had proven this, then you get this for free. But I didn't prove it. So that means you need to prove this. And the way I would like you to prove it is to use integrals. Okay? Just use definition of Laplace of some function. Right? So you'll get something like this. 0 to infinity e to the negative st h of t minus c dt. Right? So this is this. And play with it and see if you get this. You should get it, okay? We know it's going to be true because it is a special case of this one anyway. Next time, I'm going to prove this to you. All right, so that's the first question. Okay, the second question is, I would like you to find Laplace transform of this. I gave you 4 pieces. Notice there is 0 and 3 and 8. Okay, these are like your critical values, 0, 3, and 8. I would like you to write this like this first, if you can, right? Like this. If you can write this like this, you should be able to write this in this format. And then apply Laplace. Apply Laplace. And feel free to use this, okay? Feel free to use this and see what you get. So, very short assignments. I hope nothing is confusing. I hope it's understood. And next time we're going to pick up on where we left off. And we're going to solve linear ODEs. Take care.